Welcome to this presentation on how to connect and synchronize assets and digital twins using FA§ST service. FA§ST service enables you to create reactive asset administration shells by making your asset administration shell accessible to the outside world via a standardized AES-compliant digital twin API. FA$ST service also enables you to connect and synchronize your AES with the asset it represents via what we call asset connection. The asset connection is, as many other aspects of FA$ST, realized as an interface which ensures easy extensibility and the support of arbitrary communication protocols. FA$ST service ships with 3 predefined implementations of this interface for different communication protocols: OPC UA, HTTP, and MQTT. Connecting and synchronizing your AES with different assets is done via a configuration file that does not require writing or compiling any code. The functionality of asset connections is further divided into 3 interaction patterns that are realized via so-called providers: the value provider for reading from and writing to the asset on demand, the operation provider for executing operations on the asset, passing the parameters for the operation from the AES to the asset and the result back from the asset to the AES, and the subscription provider for subscribing to value changes on the asset to continuously synchronize the AES to the asset. Mapping between the AES model and the assets is done by linking each provider to its corresponding AES submodel element, in this case a property or operation. This shows the structure of the FA$ST service configuration, relevant for asset connections. As always in the FA$ST service configuration, you start out with the add class property, defining the implementation you want to use. In most cases, one of the 3 implementations that are already shipped with FA$ST service. After that, you can add any parameters to configure the asset connection. The available parameters depend on the implementation class chosen. For example, for OPC UA, one parameter would be the server address. Finally, you can define any number of value, operation, and subscription providers. They are defined as maps, where the key is the serialized reference to the AES element to be synchronized, and the value is the configuration of the provider, which, for example for OPC UA, would contain the node ID that this AES element should be connected or synchronized to. Asset connections in FA$ST offer many additional features. One of the main features is the easy integration of legacy or brownfield assets via our template and query mechanism. As existing assets often provide or require messages with a custom or fixed structure, the template and query mechanism helps to integrate them without the need for any additional tools to pre- or post-process the message structure. FA$ST service also separates between protocols and payload formats such as JSON or XML. This allows to use any combination of known protocols and payload formats without having to re-implement any of them. Furthermore, FA$ST service offers automatic reconnect on connection loss as well as basic authentication. The table on the bottom shows the asset connection implementations shipped with FA$ST service. As you can see, not all protocols support all types of interaction patterns. For example, MQTT does not have an equivalent to a read on demand operation, as it is a pub/sub based communication protocol. Finally, I'm going to show a demonstrator of the asset connections in action. For this, we will have 3 demo assets as shown on the right, one for each of the supported protocols. Each of them contains a value property and, as far as supported, an operation called add, taking 2 parameters that will be added to the current value of the value property. On the left side, we have a corresponding AES model that contains an AES property called value underscore, followed by the protocol name for each of the protocols, as well as 2 operations at OPC UA and at HTTP. We also connect the AES properties and operations to the corresponding assets. Now let's switch to the actual demonstrator. Here we see all 3 assets as well as the FA$ST OPC UA endpoint at the same time. In the top left, we see the FA³ service containing our AES data model as shown with the value, properties and operations. In the top left, we see the FA³ service containing our AES data model as shown with the value, properties and operations. First, we're going to subscribe to the three different values, OPC_UA, HTTP and MQTT. This will show us the state of the digital twin as we will be modifying the assets in the next step. In the top right, we see the OPC_UA asset with its value node and add operation. First, we're going to change the value on the asset itself from 0 to 1. Notice how the value on the digital twin also changes accordingly. Next, we're going to execute the add operation on the asset with the parameters 1 and 2. This should update the value to 4. Once we execute the operation, we see that the value is updated also on the digital twin. Now we can do the same for the HTTP asset in the bottom right. First, let's get the current value from the asset itself. This returns 0, which is correct. Now let's set the value to 1 directly on the asset by sending an HTTP put command with the corresponding payload. Again, this change is reflected in the digital twin in the top left. Let's now also execute the add operation with parameter 1 and 2 via HTTP post. And this also works as expected, changing the value to 4. Next, let's look at the MQTT asset in the bottom left. Here we can publish a message with the JSON payload, setting the value to 1 on the corresponding topic data/value, which is successfully reflected in the digital twin. As MQTT does not support executing operations, we're done here for now. So far, we have shown that the FA³ service is updated when the data on the asset changes. But how about the other way around? Will changes made via the digital twin be reflected in the assets? And what about executing operations? Let's do another test for this. When setting the OPC_UA value to 10 via the FA³ service, we see in the top right how this value is also set on the asset itself. And if we execute the add operation with values 2 and 3, we see that it successfully executes and the value is now correctly updated in both the asset administration shell as well as the asset. Let's do the same for our HTTP asset. We set the value to 10 via FA³ service. And then check on the asset itself that the value has been updated to 10, which it is. Now again we execute the add operation with the parameters 2 and 3 on the digital twin. We see that the result is successfully updated in the digital twin and also reflected on the asset itself. Setting a value on an MQTT asset connection via FA³ service is less spectacular. This is because an MQTT server typically is separated from any application logic and only acts as a message broker. So to check if updating a value via the digital twin works, we're going to subscribe to the corresponding MQTT topic. Once we update the value on the digital twin, we expect that a message will be published on this topic. We now see is the case and the new value is correct. This concludes this demonstration and presentation on how to connect and synchronize assets with digital twins using FA³ service. Thank you for watching.